Extreme Physics.
This is going to be an exercise in learning how to reason with circuits. Here I have a circuit board, and it's nothing more than a block of wood with pegs pounded into it. These pegs aren't connected to each other electrically. They're just there as convenient connection points, right? With the circuits, we got to connect a lot of things, and you couldn't do it with your hands easily. So let's take a look at this a little deeper. I have these battery holders. They're nothing more than a convenient way to touch one wire to one end of the battery while the other touches to the other. They're made out of metal, so that's a little deceiving. They just did that, I think, because it's cheap. But if you take a look, there's insulators, so the wires aren't actually touching to the metal. So the metal for the holder of the battery itself is not being used as a conductor, just the end pieces. So the top of the battery is connected to one of the wires and the bottom to the other. All right. So then we have a 1.5 potential difference between those wires. And now I connected them to the posts. So now we have a 1.5 volt potential difference between the posts. And that'll be convenient to connect other electrical devices to. So I'm going to take another battery and also 1.5 volts. And we have a voltage gain of 1.5 volts across the first one, 1.5 across the second. And so altogether, we have a voltage gain of 3 volts. And now I'm going to add one more 1.5 volt. And we have 1.5, 1.5, 1.5. So we have 4.5 volts between the two far posts. Okay, we're going to make a connection to these posts by just putting another wire there. And all I'm doing this is just making it convenient because what I want to do is get my electrical connections closer together so I can connect them to light bulbs. And there you go. So I have 4.5 volts between here and here. And since they're connected, we also have 4.5 volts between there and there. I'm going to want to connect two bulbs in parallel. So I'm just going to extend this even further. So 4.5 volts between there and there. 4.5 volts between there and there, and 4.5 volts between there and there. All right, so I'm going to take my first bulb, which I've labeled A, and I'm going to put a potential difference of 4.5 volts between it. But first, let's take a look. We have our socket here. This has two purposes. It makes a mechanical and it gives an electrical connection. We wanted to put our voltage from the little nubby to the little screws on the side. So let's see how this works. If we take a look at the side, we can see that how the bulb just screws in. We got that little corkscrew thing, and that matches the bulb perfectly. So that is both a mechanical and an electrical connection. If we take a look, we should be able to see that there is a connection between the side and right there, from the side all the way out to this wire. Now, we also need to connect to the nub. So how do we connect to that little nubby thing? Well, if we take a look on the side, we can see on the other side of the holder, the wire is not connected to the corkscrew side. We see there's a red insulator right in there that's insulating the corkscrew portion to that bottom connection. We can see the red insulator right here. And coming through the bottom, we can see that little thing, that little bump there is actually connected to that electrical part on the outside, which is connected to the wire. So that actually makes a nice electrical connection with the nubby, right? So there we go. So all we need to do is put a potential difference across those two sides, and we will get current flowing through the light bulb, and it will light up. The filament will get nice and hot. Let's see if you can see the filament. You can see it a little bit there. See the filament? Very small, and that gets really hot and lights up. So let me put 4.5 volts across this bulb, and we can see that when we do that, current flows, and the filament gets hot, and it lights up. So now we're going to connect a second one. It's a different bulb. You can see it's physically smaller. It's actually brighter. It's significantly brighter than the first bulb. B is brighter than bulb A. They have different characteristics. What we want to figure out is through electrical reasoning, can we figure out something about bulb B relative to A so that if we put them in a different configuration, if we put A in series with B, what will it look like? We know that when we put them in parallel with each other, that B is definitely brighter, right? So, but what will happen if we connect these in series? And that's going to be our goal, is to do some analysis and make a prediction, and then we can test it and see if it works out. So again, what we're going to do is we're going to rearrange the circuit in a moment, but first we need to make our prediction. We're going to put A and B in series with each other, and we're going to make a prediction which is brighter, and hopefully when we connect them, it'll be really clear. Okay, so we have a 4.5 volt gain, and then across A and B together, we will get a 4.5 volt drop. Not necessarily the same drop across A and B, but the combination together must have a 4.5 volt drop because we have a 4.5 volt gain across the batteries. All right, let's do some advanced thinking. Get yourself a sheet of paper. Gonna really need a good effort here to get anything out of this lesson. You can't just follow along. You have to actually do it. Otherwise, you're really not getting anything out of it. You're wasting your time if you're just going to watch. So make sure you have your circuit drawn. We got A and B. They're connected in parallel. And then why don't you also make a chart? We're going to need to do a comparison between A and B. We need to figure some stuff out. We're not going to do any calculations. We're just going to use reasoning. Oh, that's some tough stuff. All right, let's take a look at some electrical parameters that we've studied. We've studied, of course, voltage, current, and resistance, and we also power. Let's do our analysis with those. And what we want to do is we want to see, with some of these we're going to know nothing, really, and some of them we're going to know a bunch of stuff. And there's one of these that we're really going to want to know because we want to know what electrical characteristic that exists in this circuit will also exist when I connect these in series, right? What electrical characteristic follows the device, all right? So we're going to need to know that, and we're going to need to figure out what that is so we can carry it over to here. This is what I want you to do. If let's say I knew the voltage of A because I look at a parallel, and since this is closer to the battery, I know the voltage of A is bigger than the voltage of B because B is farther away. So I would put a big V for A and a little v for B. Okay, of course, this is just totally bogus. That's not true at all, but that's the sort of thing you do. If one of them's bigger than the other, make it bigger. Draw the letter bigger. If they're the same size, draw them the same size. Right? And if you don't know anything about the relationship, don't put anything there because we don't know anything about that. So why don't you take a moment to do that now? Put in a real good effort.
Pause the video now.
All right. So erase that voltage thing because that was completely bogus. Hopefully you know that the voltage across A is the same as the voltage across B. So I'm going to draw the same size V. All right, so they're the same size. Boom! Current. Well, I know the current isn't necessarily the same, but I don't know. I don't have a relationship with current. We're going to skip that. Resistance. Well, I know resistance is a property of devices and stuff like that. And this is something that's going to follow the device. If I take it to the other circuit, if I can figure out which one of these has a greater or less resistance, it will also have that in the series circuit. So this is kind of what I'm looking for, but I don't know what that is yet. Power. Well, power is how much energy something uses. Could you tell which one was using more energy? Was there any clue? Right? Well, actually, in the old days of incandescent, when I was a kid, and we had incandescent light bulbs, if you wanted to know how bright it was, you'd say the power. a 100 watt bulb was brighter than a 60 watt bulb. All right. So yes, power, the brightness, and how much energy is it using? One of those is definitely using more energy. It was the brighter one. And which one was brighter? B was brighter. So B used more power in this circuit. All right. Now, and we want to know resistance. So we need to find a relationship between voltage, power, and resistance. Why don't you take a moment to find one and see if you can figure out which one of these had a greater resistance, which one had less resistance.
Pause the video now.
All right, using your Regent's reference table, you should have found that power equals V squared over R, right? So therefore, solving for R, I get R equals V squared over P. So let's see which one had greater resistance. So we got the voltage is the same in both of them, so equals V squared equals V squared, same size. Power, well, this had a big power, and this had a little power, right? So this must have had a big resistance because we had a small denominator, big numerator, and boom! Bigger resistance for A than B. All right. Beauty. So why don't we take a look at do something similar with our series circuit. I'm going to go with a different color. Why don't you do the same thing with the series circuit and figure out which bulb is going to be brighter. Why don't you do that? It's going to be the chart's going to look different. There's one thing that's going to be the same, but that's it.
Pause the video now.
All right, here's our new situation. We got A and B, we got a battery, and well, we know the voltages aren't going to be the same in this circuit. We know that this voltage equals the sum of those voltage drops, but so we don't really have the voltage thing. Current, though, we do know this is a series circuit, so there's only one path, so the current must be the same everywhere. Right, there we go. Hopefully those are about the same size. So we got current. So what do we have? All right. So we didn't know anything about that. We had that, and we know the resistance, right? We know that A resistance is bigger than B resistance. All right, and we want to know brightness, which is power. So we need to find a relationship between power, current, and resistance. So we got, I think, if we look at our Regent's reference table, we get P equals I squared R, like that. So let's see how that works out. Well, both of them have the same I squared. I squared. Big R. So we must have a big P. Little r. Little p. And so it looks like A should be brighter than B. B's less bright. All right. Well, let's go see if it works out. Okay, this is the moment of truth here. Let's connect it in. Oh, look at that. A looks much brighter. In fact, B doesn't even look like it's lit at all. Maybe it's not even the circuit. Maybe this is a trick. Oh, no, it's not a trick. See, I unscrew it, and that breaks the flow, the circuit, and it's back in. Well, maybe it's because B is closer to the negative end of the battery, and the electrons get there first. So let's just switch the order. Maybe the old switcheroony will work. And no, it didn't make a difference. That was a bad idea. Okay, it looks like A is just A is brighter. That's what we predicted. lower resistance. Let's actually check the voltages. You'll see that the voltages aren't quite 1.5 volts. They are if there's no load, but when I put them under a load, the voltage drops a little bit. So we could see instead of 4.5 volts across, we only had 4.4. Let's see how much is across A. Almost all the voltages dropped across A, and that makes sense because the current was the same everywhere, and the one with the higher resistance is going to have the higher voltage drop. So that's why B didn't light either, because there was very little voltage drop across. You could see only 0.2 volts. All right, that was an interesting lesson. I'll see you soon.
Extreme Physics.